Okay, so I'll record this so that you guys can review it later, and then so Lawrence can jump in. The session is going to be held on Saturday and Sunday, 8 a.m. It's in the Brown is the name of the building. The last name is Brown. It's the Petroleum Building. I'll try and rustle up a map there at Marietta College. I know you, Jake, are you familiar with where Marietta College is? I think you're local here.
I'm from Parkersburg.
Okay, so you're allowed over the river. You've got a passport and everything, right? So
yeah, yeah.
So yeah,
I don't go
Marietta
to
College.
Ohio often, but
yeah, it's not that big a place. It's
yeah.
right on the south end. I'll get a map and circle it and send it to you guys by email. But it's the Petroleum Building. It's right there. Marietta College has like a walkway that goes down the center of it, like a concourse area where you can walk down. And one end of it is like Putnam, and I forget the other end. I forget what that street is. It's closer to the other end, away from Putnam, and it's right on that middle concourse. I think there are only like 10 or 15 buildings there at Marietta College, so it's not. It's the building that's got a oil grasshopper derrick thing right out in front of it.
Okay.
So anyway, I'll send a map. So we're going to start at 8 o'clock there. Hopefully security will let me get in because the college is closed right now, but Chris Jacobs had promised me that we'd be able to get in. So we'll start there. I haven't quite figured out what we'll do for lunch on Saturday. Maybe order a pizza, or if you bring something, whatever. Sunday, we usually we'll play that by ear, but we might want to plan on you just bringing something on Sunday, because we're going to get done hopefully pretty early. So not early, and we'll go straight through rather than break for lunch. So we'll get it done. Okay, so I promised here that we would go ahead and jump into chapter 7. Let me go to the screen share. And okay, it seemed to me we had I got to sort of go through this. Well, we'll do it quick, as opposed to me just shooting down through. If the voltage drop is too great, what can the designer do to fix the problem? Well, increase the size of the wires, right?
Right.
Mm-hmm.
Yep. Which of the following is considered the maximum? I'm going to have to lower this down because my camera is blocking it. The maximum current a panel could use. Better go. All right. So that's going to be the short circuit current, right?
Mm-hmm.
To account for the inefficiencies in your system, you always have to derate it. I'm jumping through these first ones because we did these last week. So when an unintended pathway is created between the PV array and the grounded surface, this is known as a ground fault, right? So that's like if the wires are being pinched or shorting out somewhere. When sizing a battery bank, its capacity is in amp hours, typically. Which of the following is not a circuit in a typical grid-tied system? Well, it goes PV source, PV output. So here's a typical system. The source circuit is between the panels and the combiner or the junction box. From the junction box to the DC disconnect is the output circuit. Then from the DC disconnect to the inverter is the inverter input circuit. And then all the AC is the inverter output circuit. So that's just the terminology for the various circuits that are in the system. The maximum nominal voltage a residential grid-tied system can be configured to by code is
600.
600 volts, right? That's residential. In the US, it varies elsewhere.
What's commercial and industrial then? What's the utility scale?
I always get
Is that
mixed up with the
1,000?
European. It's 1,000, I believe.
Okay. Okay.
Yeah. Now
good
ground
job,
mounted.
Jake.
Pardon?
Jake answered it. I was like, good job, Jake.
There you go. Yeah. And ground mounted systems commercial don't really have that limit.
Okay. Oh, really? Commercial ground mount systems don't really have a limit.
Right. But because the equipment that's available, it's typically going to be 1,000.
Sure, sure.
The maximum DC nominal voltage accessible for a standalone, the battery bank in a standalone is?
24?
No, 50 volts, right?
Oh, 50? Okay.
Remember, 48 volt is going to be usually the main size.
Yes.
So 50 volts is actually the limit. EMT conduit stands for?
Electrical metallic on
Electrical metallic tubing.
Yeah.
To determine the maximum panels in a string, you must know all the following except the azimuth, the coldest temperature, the voltage input specifications of the inverter, or the temperature coefficient of the panels.
It's the third one.
He says it's the voltage input specification at the inverter of the inverter. I'm sorry, I can barely read it.
Oh wow.
Oh, I was wrong.
The azimuth. Yeah, when we're dealing with maximum panels, and this is going to be one of the math problems that we'll get to here in a little bit, the way you calculate it is the first step you do is what is the coldest temperature ever experienced at that site? And then you take the delta or the difference between STC and the coldest temperature ever experienced. And that tells you in number of degrees Celsius. Now, the temperature coefficient is how much voltage changes for every degree Celsius, as temperature changes. So
Right.
the temperature coefficient is usually in the 0.4% per degree Celsius. So if it increases as it gets colder, 0.4%, then we need to know how many degrees. So that's the delta. So we multiply the number of degrees times the temperature coefficient, which is how much the voltage changes per degree. And that's going to tell us what is the voltage change on the coldest day ever experienced. So for example, if the temperature coefficient is plus or minus 0.4%, then if it's 0 degrees Celsius freezing, that's a 25% delta. So you'd multiply 25 times 0.4 and you'd end up with 10%. So it would be 10% more voltage produced by that panel on the coldest day because it's getting colder, right? 10% more voltage there if the temperature was 0. Well, then what I need to know is what is the maximum voltage that panel might produce? Well, that's going to be VOC. So I multiply VOC times 110%. I'm just doing this out in the air, so don't worry if you're not following me 100%. But so then I take the coldest temperature. How much is it going to increase? In this example, we said 10%. So I take the VOC times 110%, and that's the voltage that could theoretically be produced by that panel at that temperature. So then I know now that let's say the voltage of the panel was 40 volts. So now on the coldest day, that might produce 44 volts. Well, now I need to know what is the input of what's the maximum voltage for that inverter? Well, if the maximum voltage for the inverter is 600 volts, I divide 600 by 44, and that'll tell me how many panels I could hook up before I exceed that voltage. All right, so that's just a long way of getting to the fact that I don't need to know what the azimuth of the array is to figure that out. But I do need to know what's the coldest temperature ever. I need to know what's the voltage input for the inverter. And I do need to know what is the temperature coefficient of the panel. Okay, we'll get into these exactly, but hopefully by me walking through that, it'll help you when we get to it. I don't expect you to remember or memorize those steps, but
that is on the test, correct?
yeah, and usually the way I think it's a help is if you can remember what's the first step, you can usually then walk your way through just logically.
Okay.
So with the string calculations, the first step is what's the difference between the temperature, the hottest or the coldest, and STC. That's my first step for that.
Okay.
I'll get into it here in a second with a real world example and you can see it. So
Okay. Okay.
all grid tied inverters must,
UL
So
1741.
UL, yeah.
yeah, it
Oh,
must
yeah,
be
yeah,
UL
1741.
1741. And if you were on the call earlier today, now it's going to be soon 1741 SB
Yeah.
is the newer version of this standard.
So what were you saying the SA is the older version and then SB is the newer version?
Yeah, SA came out to deal with smart inverter issues, and it came out only a couple of years ago, and now it's going to
Right.
be superseded by SB.
Right.
Um,
Right. Okay.
Yeah, and I think they just put B there because it was supplemental amendment or addendum, which the SA stood for. SB, I think, is just that B comes after A. I don't think it's anything more than that, you know.
Gotcha. Well, it works. It's understandable.
All right, if you have a wire length of 100 feet and a 90 volt, 8.5 amp D-rated DC circuit, what is the smallest wire size you need?
Give me 90 volt, 8.5 amp.
100, and so it'd be
How many feet?
100.
Yeah, 100 feet. So let me show you, I'll jump in with the whiteboard.
Smallest wire.
Well, it's only gonna.
I remember the answer, but that's only because I just took this test the other day.
Yeah. So what was the question? It was
Now we're derating for the 100 feet voltage drop. What
yeah,
is it, Jay?
Yeah, the question was it's what's the voltage drop equation? That's what we're solving for.
Well, it's basically amps times resistance divided by or times 2 divided by 1,000.
Twice the distance divided by 1,000 feet, right?
Yeah, I think so. Right.
All right. So we know what the amps are, right? The question says it's 8.5 amps.
Right.
What is the resistance? Well, that's something we've got to get from the answers. So we'll leave that blank for a second. What is the distance? It's 100 feet, right? So 2 times 100 is 200 divided by 1,000 is going to be 0.2.
0.2.
Did everybody understand how I got that?
Okay.
Twice the distance is 100, 200 divided by 1,000 is going to be 0.2. So now we need to know what is the resistance. Well, it says number 6 wire has a resistance of 0.510. Okay. Everybody clear where I got that from the answer?
What was that?
A.
Yeah, it's from the answer in A. It says number 6 wire with a resistance of 0.510. So what's 8.5 times 0.51 times 0.2?
8.5 times
0.51.
0.510
Yeah, times 0.2.
times 0.2. 0.867.
0.867?
That's what I got.
That sounds about right. All right. So is that less than 2% voltage drop on a 90 volt circuit?
So you got to divide that by what, 90?
Yeah. So 0.867 divided by 90.
It's only 1%.
Yeah, it's a little bit less than 1%, right?
Yeah.
All right, so that qualifies. So then the question is, does the next one?
Yeah, you just gotta keep doing the math.
Oh,
Yeah.
okay. Which one's gonna be the best? We're looking for the
Yeah,
best
so
answer?
the next one is instead of 0.510, it's what, 0.809? Is that what it was?
I don't remember.
We can't see it. Oh, I might have it.
Yeah, 0.809. All right.
0.09 times 0.2.
So now it's 8.5 times 0.809 times 0.2 gives me
8.6.
no, that doesn't sound right. 8.5 times 0.809 times 0.2.
Oh, 1.37.
1.37. All right, so what's 1.37 divided by 90?
Divided by 90.015.
0.015 or times 100 to get to your percentage, it's about 1.5%.
1.5.
Yeah, 1.5%. Right? Is that less than 2?
Yeah.
Yeah, so now the answer is B, but we have to see if C works. Well, C has a resistance of 1.29.
1.29. So resistance is 1.29 on.
So 8.5 times 1.29 times 0.2.
It's 2. That's way out. That's it, but that's way out.
So what is
8.5 times 1.29?
Oh shit.
times 0.2?
We got 2.193. So
2.19 volts. So 2.19 divided by 90. Well, if it was divided by 100, it would tell us that it's over 2%.
right.
So it's
We're-
going to be
we're
even
definitely-
more.
Right.
So this one is actually
So
greater.
B is our answer.
Yeah, B is the answer.
And that's pretty easy to get.
Yeah.
You just
All
gotta
right.
do it. So that's not hard. I understand.
Yeah,
the-
it's just the difficulty
No,
there is
on
you
test is just like the equation, or we're gonna have to make a formula for it with the test.
what's you broke up a bit. Are you asking you've got to remember the voltage drop equation?
Okay. All right.
Yeah, you're not going to get a cheat sheet with equations.
I asked for it.
Yeah, you wanted it.
tried to. We all asked
So
for it. So
the
don't
three
feel alone.
equations you got to remember are watts equals amps times volts, the power equation. You need to remember Ohm's law, which is volts equals amps times resistance, or VER. And then you have to remember the voltage drop equation, which is VER adjusted for distance, right? Volts equals amps times resistance times twice the distance divided by 1,000. Well, why is it divided by 1,000? It's because the NEC gives us resistance in ohms per 1,000 feet. And why is it twice the distance? It's because it's there and back. The circuit is a round loop. So if it's 100 feet from one end to the other end, it's 200 feet of wire in that circuit. And we're given the resistance per 1,000 feet. So it's 200 feet divided by 1,000, or 0.2 of whatever the resistance is that they gave us. So, if you wouldn't have to go through that resistance or that distance thing if you just measured the resistance on the wire instead of taking it from the NEC. But you're not going to do that. So
Yeah, we don't have measures.
yeah, you don't have the proper tools there. You won't get
We
an
don't have a
accurate.
measure. No.
You won't get an accurate reading. Okay, so let me jump back in here. All right, so we know the answer here is B. Right? To power a 24-volt water pump with a 12-volt battery, you need to add a
24 volt.
Wouldn't it just be a DC voltage
To
converter?
power a 24 volt.
Yeah, it's all DC.
It's a DC voltage converter. It would be a better solution to just get a second battery and hook them up in series.
Yeah, that's what I was looking for.
Yeah, but that's not an option here. And the
What?
reason it's not an option is on this next question. If we wanted to convert us, if we wanted to put together a solar electric fence
Mm,
and it's a 12-volt battery and you test it and you find that it's generating what is that? It's hidden from me, but
I can't see it either.
your solar panel.
2000-volt electric shock, then what do you need? What do you need to configure your system?
Well, we don't need anything AC. So the AC
those
disconnects
cancel.
out and the inverter is out.
I know the
Right.
answer because last week.
Yeah.
Uh,
So it's gonna be D if you just eliminate all the AC
Yeah, okay.
stuff.
Because there's
Yeah.
no AC before the top two's out. I can't remember what the difference is and why it's D, but I knew it was
PV
D.
panel, charge controller.
You don't need an inverter if it's not being changed from DC to AC.
Right. Everything's DC in this system.
Oh,
So if
yeah,
you just
got an
think about it
inverter on there.
logically,
Yeah, right there,
Okay.
inverter. Yeah.
you got
I
a
see it.
panel, a DC disconnect, a charge controller, a battery bank, and a voltage converter. That's all you really need. All right.
Right.
An array. I'm gonna move this down here. An array of 24 panels, each with an ISC of 8.35 amps, is configured into 4 strings, 6 panels each. The wires from these strings are combined in a combiner box. What is the minimum ampacity required for the PV output circuit? So for this one, it's 8.35. So if
You take it off.
what I would recommend you do is draw it. So like what it's saying is, all right, we've got a solar array and we're coming in with 4 strings into the combiner box, right? And each string is 8.5 amps coming in. So what is the ampacity rating of this, which is the PV output circuit?
It goes on to 8.35, but there's a D rate or something like that.
Okay, now this is a string inverter, so we're also assuming this is the DC disconnect, and then this is the inverter. So there are no electronics in front of this.
So you got time about 1.25.
Okay, so what do we do with the 8.5?
And then again, 1.25 because it's solar.
2 times. Okay, so
There's 4 of them, so we'd have to.
let me see. So 8.35 times 4, right? Equals 33.4 times 1.25 equals 1 times 1.25 equals 52 amps.
Oh, wait,
52.19. 52.19. D.
There you go, right? So what we're dealing with here is, and I usually do it backwards, I'll say 8.5 for this one. We have to multiply it times 1.25 for the NEC safety factor. You just do that for all wire, right? Jimmy and you guys know that, right? If you're going to run 16 amps, you got to have a 20 amp rated wire.
Right.
And then you multiply it again by 1.25 for solar, the variability of solar.
Ready?
So if we did that 8.5 here times 1.25 times 1.25, we would get, what is that, 13 point?
52. Oh, I'm sorry. Go ahead. I bet.
No, what is it?
Oh, it's the other way.
Oh, he's doing the other way.
He's doing it the way I would have done it. It'd been like 13 something times 4, and it gave you your other answer.
Yeah, it's 13 point.
Can't remember what it
My
is. It's
calculator.
13 something.
What's the numbers again?
8.5 times 1.25
8.5 times 1.25 equals
Times
13.28.
times 1.25 equals 13.28. Yeah, that's what we
times that
got.
by 4,
And multiply it
And
by
then
4.
multiply that by 4.
53.1.
Yeah. How did I do it different?
You did it times 4. You'll get the same answer.
Oh,
It just depends. All right. So
you
so
did
the answer.
1.25 in between it. I got you.
Yeah, I do it first and then times it by 4 because
Gotcha.
you got to times it like
Okay.
even though it doesn't give us the exact, but I would put 52.19
So
because
you
it's
round
close.
up. Sure.
Yeah.
Yeah.
So there's your answer, right?
Right.
Now, the reason I got to jump a question here, but if the wire in the PV array is placed in conduit and is exposed to sunlight, the ampacity rating must.
If it's in conduit, doesn't it say the same?
Well, it's in conduit. Basically, it's saying this question is trying to just get you to understand that when you expose wire to sunlight, its ability to carry amps decreases.
Because of the heat.
Yeah. So we'd have to increase the size of the wire or the ampacity rating of the wire when we expose it to sunlight. It's sort of like on the install that we did over there, that conduit that went out across the roof,
Right.
is exposed to sunlight. So we normally would have to be concerned about that, that it's but because the ampacity of the 6 panels was only like 7 amps.
Yeah, 1.5 of each on each, right?
Yeah, so then we had 10 gauge wire, which had a rating of 30 amps, so we were fine. But if it were close, we might have to put a bigger wire there because that wire was exposed to
Well,
sun.
he's actually good to add a few more panels. Correct?
Oh yeah, but there's just no space.
Yeah.
I
He
mean,
can
you
do it
could
on the
add
flat part.
one, but that's about it.
Yeah.
All right. So then here it says you've installed the 24 panels. This is the same question. So what it's saying here, let me jump back to my whiteboard, is it's saying, yeah, well, here we go. So what it's telling me is this combiner box, these wires here are exposed to sunlight, but the combiner box is not. So
Okay.
what will be if there's a circuit breaker in here? What
Yeah.
is the ampacity? What size circuit breaker do we need to put in there?
Which of 15 is 8.25?
What'd you say?
I was just reading it again. I guess it would just be the 4 strings. I mean, the 4 strings, the 4 8.35s combined, right?
Yeah, but what we're going to put a breaker in this combiner box.
Right. Right.
What
So
size
it'd be-
breaker do we need?
Well, what was the 4 times 8.35?
Now, each string is connected to a breaker.
And they're being exposed to the sunlight, so it would
10
have to
amp
go.
breaker. 10 amp breaker.
Yeah, we can.
Yeah.
When we do the combiner box in the lab on Saturday, you're going to see that we're coming into let's say we've got a DC or a combiner box here.
Yeah.
And the way it's set up is I've got 4 circuit breakers and my positive wire from each string is connecting into each of these breakers like this. and then they're being hooked together in parallel up here, and then it leaves to go to my DC disconnect. So that's the combining part of the combiner box.
Right.
Then all my negatives get connected in a negative bus bar, and all my grounds get connected in a grounding bus bar. But my parallel connections are being made. So I'm coming in. So what size breaker for each of these breakers would I install?
Just a 10 amp breaker, right?
Well, what's the ampacity rating with all of the safety margins?
Oh, the 1.25, 1.2. So a 15 amp breaker. basically.
15 amp.
Yep. So I
Okay.
need 4 15 amp breakers there. You always round up to the next available commercial size.
Okay.
So that's what that question is asking. So it's a little bit, so the red herring there is that the fact that it's exposed to sunlight doesn't make any difference because the combiner box is not.
Right.
You know, it's
Okay.
saying placed in conduit. You need bigger wire because it's exposed to sunlight, but the breakers doesn't really matter because they're not exposed to sunlight. What would happen if that breaker box, that combiner box was exposed to sunlight? What would be one of the issues you might run into?
The temperature.
Just heat.
Yeah. Well,
Heat.
what happens to breakers when they're exposed to excessive heat?
Well, yeah,
They fail.
they open.
Yeah, what you may get, just like wire, the ampacity load gets reduced. So I might have a 15 amp breaker that, because it's in the sun, keeps tripping when it hits 10 amps.
Yeah.
Yeah. So you're going to get some nuisance tripping. So you want to keep your breaker boxes and all of that stuff out of the sun if you can. Otherwise, you're going to get some nuisance tripping. Sometimes you don't have any choice. It just has to be where it is. Like, for instance, the build we just did this weekend, that box is over there on the west side of the building. Well,
Yeah.
it's in the sun. You know, is that going to cause a problem? If it does, then the solution would be to build a little shade awning over it. You
You're
know,
talking
just
about the
shade it.
combiner box on the
Yeah,
on
that
the
combiner
wall?
box there has some breakers in it,
Right.
right?
Right. Yeah.
So they may trip, you know, on a really hot day with the sun beating on that thing, it becomes a little solar oven.
Right.
So if you're troubleshooting a job and for some reason they keep getting these nuisance tripping on hot days, it may be that it's because the system is exposed to sunlight.
Okay.
All right.
Good to know.
Yep. All of this is good to know, right? Okay, an AC disconnect should comply with all the following except: isolate from the grid, be located 10 feet away from the point where the PV connects to the grid, be externally operable, be marked.
It's gotta be within 10 feet, right?
Right, within 10 feet, not 10 feet away.
You tricked me last week with that.
That's right. A charge controller must be compatible with all the following except. Well, what does the charge controller connect to?
The battery
And
the like from the combiner box.
yeah, so basically it's connecting the array
Yeah.
to the battery, and it's controlling how it charges. What in this list is it not connected to?
The
Harder.
All that a charge controller does is control how the power from the array goes into the battery.
yeah.
We don't care if there's an
It's not
inverter.
from the inverter. Yeah.
Yeah, we don't even know if there's an inverter. It has nothing to do with the inverter. It's only dealing with the array and the battery, so it must be compatible with both. What does a load diverter do? It's part of the charge controller typically. So a load diverter basically redirects any excess power that might be available to a load dump. So for example, with a grid tied system, the grid is always the load dump. If you don't need to
Okay.
use the power, it just goes onto the grid. But in a standalone system, you know, if you don't need the power, it's just not going to be used. It's not going to be generated. So rather than just wasting that opportunity, they typically will have this load diverted into the hot water heater to offset gas or
Oh, okay.
wood or whatever. So it's just a way to not waste power that you could be generating. Which of the following is not a factor in determining the size in amp hours of a battery bank?
The sunlight isn't.
Right. Yeah,
It's
peak
not
hours
gonna.
of sunlight is not an issue. Basically, the formula for batteries is you take your daily load, which is going to be in watt hours, you divide that by the voltage system, which of the system, which is going to give you amp hours. Then you divide that by the days of autonomy, or you multiply it by the days of autonomy. You divide it by the depth of discharge and divide it by the inverter's efficiency. So that's the equation that you would use for that. Well, you don't need to know how many hours of sunlight are there. A standalone PV system has the following characteristics. A 3 kW array, daily load of 10 kilowatt hours, maximum power draw of 2 kilowatts at any time, 1400 amp hour battery, nominal voltage of 48 volts, 4 hours of peak sunlight. What is the minimum power rating required for this inverter?
2. That's the
2.
maximum.
Remember, I beat this into you last week, right?
Yes, you did.
What determines how a standalone inverter is sized? It is maximum power draw, right?
Right.
Because all the power you're using gets pulled through the inverter. What determines the size of an inverter for a grid-tied system? Well, it's related to the array because all of the power from the array gets pushed through the inverter, but not all of the load, because you could be drawing from the grid as well as from your inverter. And if your inverter is producing more power than you need, it goes to the grid. So with a standalone system, the inverter is always sized based on the maximum power draw, which in this case is 2 kilowatts. And with a grid-tied system, the inverter size is always based on the size of the array. Okay. What is the largest grid-tied array? Assuming that the power matches the output from the inverter, that can be load side connected to a 100 amp rated service panel with a 100 amp service from the utility. So this is the 120% rule, basically, for service panels.
It can be 120 amp.
What is the largest grid tied array?
Right. Well, let me show you the whiteboard here. This is something. So what we're saying
It had to be.
Is this made by AEP? Is this something that's made by the utilities, or is this just a?
No, the NEC says if I've got a service panel, and in this example, we're saying we're coming in here with a 100 amp service.
Okay.
And the rating of the bus bar on the service panel
We
is
can be
100
feeding.
amps.
Is
right?
what?
We can put 120 amp.
Right. So the
circuit in.
120% rule means we could put a 20 amp breaker and feed it from our inverter up to 20 amps.
Yeah,
Because
that's-
the
yeah,
NEC says, you know, you might say 100 amps, 100 amp panel, it's already full. We couldn't hook up a solar array to it. But the NEC says you can go to 120% of the bus bar rating.
Okay.
So, but you've got to
Chances are
locate.
that stuff's not all gonna be on at the same time, so.
Yeah, right. They're just assuming. I mean, how many times does somebody trip the main breaker?
Yeah.
You know, quite rare. But they
Rare.
do want you to put that PV breaker as far away from the main as possible.
And why is that, Jay?
He,
Well, what they're claiming anyway, let's say these are going to load,
Uh-huh.
you know, all of these breakers in between,
Uh-huh.
they don't want the power doubling up. So this one's feeding from this direction, this one's feeding from this direction, so that the power is not going to double up onto the bus bar. You know, it's
Gotcha.
not going to, so that at any point on that bus bar, you're not going to exceed the capacity. You know, it might happen. Let's say we put this breaker up here, this 20 amp breaker up here, right next to it. You might be drawing 120 amps through that bus bar to service the load out here.
Right.
okay.
By feeding from both ends, there's less of a chance of that. All right, so we now know we can go to 120%, which tells me this breaker could be 20 amps. So what size output of the inverter am I dealing with? Well, the other thing you're going to have to assume or know is this is going to be 240 volts, right? Because it's grid tied. Everybody see that?
Yeah.
Okay. So what's 20 amps times 240 volts?
480
20 amps times 240 is 480.
or
480
4,800.
watts.
Yeah.
So
Yeah,
can I
40
put a 480 watt inverter here?
No,
Why not?
it's gonna be more than that, right? For
It's right here somewhere.
it has to be oversized, right?
No. If you did that, you'd be in trouble. Here, the 20 amp breaker, how many amps can actually be fed to a 20 amp breaker?
Well, what? Say it again. I'm sorry, I missed that last part.
Because of the NEC safety margin, how many amps can actually be fed to a 20 amp breaker?
16 and a half, something like that.
16, I think.
Oh.
If you divide that by 1.25, it's 16 amps
Okay. Okay.
will require. So 16 amps times 1.25 should give you 20.
Okay. Okay.
So I can't go more than 16 amps of current feeding a 20 amp breaker.
Well,
Everybody understand why?
Yeah.
Because we've got to have that safety margin, right? The NEC says I always want that safety margin. If I were feeding 20 amps, I'd have to have 20 times 1.25, which would be 25. So then I'd have to put a 25 amp breaker in here, which exceeds the 120% rule. So I couldn't run 20 amps. I can only run 16 amps. So what's 240 volts times 16 amps?
$3,840.
Yep, 3,840 watts. So the largest breaker or largest inverter you can put in this scenario is a 3.84 kilowatt inverter, right?
Right.
So this is one of the reasons why in string inverters, it's very common to find a 3.8 kW inverter or a 7.6 kW inverter. Right? Those are standard sizes of inverters. And that's because it's common to have a situation with a 100 amp service on a 100 amp panel, or a 200 amp service on a 200 amp panel. So that's why you get those weird sized inverters. They don't make sense until you know that. Okay, which of the following is not an advantage of a microinverter over a string inverter? They're not easily accessible for repairs, right? Randy, you were just climbing around on a roof. What if one of those inverters fails? Well, now you got to get back up there, remove the panel, pull that inverter, replace it. It's not really handy. So, which of the following equipment will likely not comply with the 2014 NEC shutdown? Well, that's just a regular
They
old
already
string
said.
inverter, right?
Yeah. Okay.
The rapid shutdown basically means it's going to shut down at the panel. So that's why we have optimizers. That's why we have microinverters, is they turn off as soon as they lose sight of the grid. I'm going to skip over this for a second. I want to get to the math questions here before everybody's brains are gone. Yeah, now we're into the math. Okay. So Jake, this is what you were hoping for. Right? Sizing an array. Assume the average US home in 2010 consumed 960 kilowatt hours per month. Assuming 4.2 hours of insulation at the site and a 90% D-rate factor, what size array do you need?
Oh my God, that's a big one.
Okay, so how do we figure out array sizing?
To the demand of the load, or how much load we need for the we're talking about grid tied system.
Yeah, grid tied system. So first thing we need to do is figure
How much
out
power
what is our
consumption?
load per day, our daily
Oh, yeah.
load.
Yeah.
So this is telling me that it's 960 kilowatt hours per month. So we could divide that by 30 or 30.5 is what I usually do, an average number of days in a month. So what's 960 divided by 30 and a half? I show about 31.47 or 31 and a half roughly. Everybody get that far?
So far, yeah.
Okay. Then what do we do? That's telling me kilowatt hours. I want to get from kilowatt hours to kilowatts. So I would divide by the hours of insulation.
This is 31.
So 31.47 divided by it. Well, it just told me it's 4.2 hours.
Okay.
About 4.2.
Equals, we got
7.9 or 7.5, right?
1.47.
7.49.
4.2.
Yeah, 7.49.
So that's the size of the array if it were 100% efficient. Is the array 100% efficient?
Well,
No.
No.
So what is its efficiency?
With the 0.9 D-rate factor.
Right. It's telling me it's 90% efficient.
Home in 2010.
So I divide 7.49 by 0.9. If you multiply it, you're going to get a smaller number. And it doesn't make any sense that if the system's not efficient, if you use a smaller system, you'll get more power. So that's just sort of a sanity check there. So if I take 7.49 divided by 0.9, what do I get?
Because that's the D rate.
8.32.
Yep. So the answer is going to be 8.33 kW. So if here on the screen, it's going to walk you through the math. So we take the monthly load,
Oh, yeah.
divide it by the days in the month, and we get 31.475 kilowatt hours per day. So that's our daily load. Now we need to have 31.475 kilowatt hours. Well, what is insulation telling me? It's saying that for 4.2 hours, I get pure sunlight. You know, it's not like the rest of the day is dark, but I'm getting 4.2 hours of insulation. So if I get 4.2 in a day and I need 31.475, I just divide that by 4.2 and it tells me I need a 7.494 kilowatt array if it were 100% efficient. But it's not. So I divide that by the D rate and I get 8.33. So this is the way you're going to size every single array. You take daily load, divide it by the hours of insulation, and then divide that by the D rate.
We'll go over them like that because these are all written at the bottom of each one.
Right.
Yeah.
So you're going to need to know those three things. This question's pretty easy because it's only given you the three things you need. You know, I mean, it didn't give you
like
any.
to make those questions where you throw all that extra BS in there.
Yeah, I have a lot of those, right? A lot of BS. But, you know, in the real world, there's a lot of
I
extra
know.
information.
You're right.
Yep. Okay, so a homeowner in Phoenix, Arizona has a daily load requirement of 9.6 kilowatt hours. So you don't have to figure out the daily load. We already know it, right? She's opted to use microinverters that produce 250 watts. She set the altitude at 25 degrees, giving her 6.54 hours of insulation. Assuming she selected a panel that will produce at least 250 watts, and assuming her system is 95% efficient, how many panels does she need to fully meet her load? Okay, well, this is, first thing is we size the array, right? How do you size the array? Take the daily load, divide it by the hours of insulation, and divide it by the efficiency, by the D rate, right? So what's the daily load?
9.6 divided by 6.54.
Right?
Divided by 0.95.
Divided by 0.95, right? That gives us a number. What number do we get?
I don't know.
Here it is right here. There's all the info.
6 divided by
So we just gotta divide 9.6
9.6
divided by 6.54
6.54.
divided by 0.95.
So 9.6 is the daily load divided by 6.54 divided by
0.95.
point.
Is everybody getting 1.545?
Yeah.
Okay, that's kilowatts. In this case, if we made it watts, it would be 1,545 watts, right?
Okay.
Are you tricking us with watts and the kilowatts? We gotta be not tricking us, but we gotta be paying attention.
Well,
I mean,
I'm just
I know the difference between the two, but like,
well, it's because in order to figure out the number of panels, I need to divide the whole size by 250 watts.
right.
So
Okay.
it's easier if I just convert it over to watts, which is
Watts,
going to be
okay.
1,545 watts
Right.
divided by 250 watts for each panel. So I end up with what?
I'm sorry.
1545 divided by 250.
6.18.
6.18. So how many panels do I need?
What size panels were they?
Well, you just did the 250.
Oh, I'm sorry, we gotta go by. Don't we gotta go by the microinverters too, though? What their output is?
Yeah, well, we just assumed that that's why I said 250 is what the microinverter is, and the panels are at least 250.
Okay, I missed that.
So we ended up with 6.18.
We'll need 7 panels.
Yeah, we need 7 panels. We can't have 0.18 of a panel.
So you round up.
So you round it up because the question said to fully meet demand. In a case like this, if you're really sizing it, you might go with 6, you might go with 7. Just depends on how close you want to get to what their demand is. But the question said fully meet demand, so you got to round up. So we're going to go with 7. Right? Does that make sense?
Yes.
Okay, now we're getting into I think this is a battery bank question, right? A cabin sits on a mountaintop in North Carolina. The location has a latitude of 35 degrees north with 4.8 hours of insolation. The daily load requirement is 3 kilowatt hours. The designer has installed a 48-volt standalone system that has been derated to 75%. The inverter is 95% efficient. So that's part of that overall derate. Temperature extremes are minus 37 and 43. The battery bank provides 2 days of autonomy and uses 6-volt, 250 amp hour batteries to a 60% depth of discharge. How many batteries did the designer need or anticipate would be required? So this is a hard question, right?
Yeah.
So how do we start? How do we start a battery bank size question? Well, to my way of thinking, the easiest way is to think, okay, where do I want to end up? And I want to end up at amp hours, right? Because my batteries are measured in amp hours.
Mm-hmm.
But I'm going to start with my daily load, which is in watt hours or kilowatt hours, right? So it says the daily load is 3 kilowatt hours or 3,000 watt hours. If I want to convert that to amp hours, what do I do? How do I convert watts to amps? Any idea, Randy?
I'm drawing a blank for some reason.
Well, what's the power equation? Watts equals amps times volts, right?
Right.
So if I want to convert watts to amps, I divide watts by
Yeah.
amp.
Okay.
No, if I want to get to amps, I divide watts by volts.
Watts by volts. Gotcha.
Right. So I've got 3,000 watt hours per day. What's the voltage of my system?
48.
48 volts. So what's 3,000 divided by 48?
I don't have a calculator on me.
3,000 divided by 48. 62.5.
Right, 62.5. So it's telling me that I need 62.5 amp hours of battery to handle 1 day of my system if my system were 100% efficient and I could use the whole battery. Everybody clear with that?
Yeah.
So for 1 day's worth of power, I need 62.5 amp hours for a 48-volt amp hour battery. If I could use the whole thing and if I only needed it for 1 day and if it were 100% efficient. So how many days do I need this?
Two days.
Right, 2 days of autonomy. So I take 62.5 times 2, And now I need 125 amp hours, right?
Right.
If I could use the whole battery and if it were 100% efficient, but I know it's not. How much of the battery am I going to use?
75%.
No, how much of the battery? What is my
Oh,
depth of
60.
discharge?
60, my bad.
60%.
Yeah, I'm only able to use 60% of the battery's energy, right? So I take 125 and I divide it by 0.6.
6.
If I take 125 and I divide it by 0.6, 60%, which is 0.6,
20.8.
208.
I'll do it backwards.
It's 0.6, not divided by 6.
Oh,
It's
I
divided
must
by
have missed the decimal.
0.6. Because it's 60% is
Yeah.
0.6. Right? So I need 208 amp hours, but it's not 100% efficient. Well, what am I dividing it by? I'm dividing it by the inverter's inefficiency.
The 75%.
No,
Or
not the whole
95%. I'm
system,
sorry.
the
I'm sorry.
0.95. So I divide it by 0.95. Why do I divide it only by the inverter? It's because the inverter is the only thing between the battery and the load. So that's the only efficiency I'm worried about at this point. So I end up at 219 amp hours. So how many batteries do I need to provide 215 amp hours? 219 amp hours. Well, the battery that we've selected is 250 amp hours. And I need 219. So I
one's
only
enough.
need one string, right? Does that make sense?
Mm-hmm.
Because I need 219, but it's providing 250. So I'm going to have a little extra capacity.
Okay.
But how many batteries in a string? It's a 48 volt system, but the battery itself is only 6 volts.
So 8.
Right. Because I got to hook up 8 of them in series
To get 48 volts.
to get 48 volts. So the answer is going to be 8. You could have seen, if you just looked at this and you saw that the battery selected is a 6 volt and the system is 48 volts, well, then the only two answers that could possibly be right are C and D.
Yeah.
Because they have to be multiples of 8. You know, it couldn't be A or B. So right there, you're at a 50-50 guess, you know, at that point. So what I'm really hoping you're going to get out of these questions is begin to logically think through, what am I trying to achieve here? Not what am I trying to get the right answer? It's like, what am I trying to achieve? And can I puzzle it out?
Okay.
So you guys are going to need to
Oh,
work through these questions a
You know what it
lot.
was? Well, Heather's actually volunteered to sit in with us a little bit this week and help us try to get the math part down.
That's right. If only she was a professional teacher, that would be so much more helpful, wouldn't it?
It would be nice if she was here right now to overhear you saying that, but she just walked out the door. But I will pass the message on.
There you go. So she knows how to deal with children who are struggling, right?
Yeah, and
I am
much
a child that is struggling.
Same thing when it comes to a bunch of dudes struggling.
Yeah. No, I'm a child struggling.
There you go. Okay, which of the following would not be a factor to consider when derating the system? Inverter inefficiency, total solar resource, soiling, or voltage drop?
The total solar resource. So that's
Right.
not something that would happen over time.
Right. The total solar resource is just how much sunlight is available, how much energy is available if everything was perfect. So that's not an inefficiency. When we talk about derating, we add up all of the things that are going to reduce the efficiency of the system. It could be
Over time, the panel's losing
yeah, over time they do degrade. They could get dirty, they could get covered in bird poop. There is voltage drop. You know, whenever you hook up wire over distance, you're going to lose some due to resistance. There's going to be resistance based on connectivity issues like at switching and things like that. What are some? Oh, system downtime is another one they factor in. If you figure over the course of the year, you're going to be closed for a week for repairs or something, well, then 1/52 of the generating capacity over a year is going to be lost or should be derated for. Snow covering is another issue. You know, lots of inefficiencies that can creep in. Panel mismatch. So in this case, the answer is total solar resource. That's not an inefficiency issue. A system has been designed with an 8.5 kW solar array and a 7.6 kW inverter. The system is said to have a 1.19 what?
So it's been designed 8.5 kilowatt solar array and a 7.6 kilowatt inverter. This is to have a 1.19 inverter load ratio.
That's correct. Yep. And in today's market, we're looking at about a 1.3 inverter load ratio. So for instance, if you had a 10 kW inverter, you might have a 13 kW array. You know, that's just where it operates at its most economically efficient.
Okay. So
that's-
the array's oversized again. Why?
Well, yeah, it's because of clipping. So basically the logic there is if I've got an array here, over the course of the day without any clouds, so this would be dawn, the array is going to generate power at something that looks like that. It's going to be just a standard bell curve, right?
Okay.
So this would be solar noon right here.
Okay.
When the sun is directly overhead. All right. So if let's just use a microinverter as an example, but this could be a string inverter as well with different numbers. But let's say that I've got a 250 watt panel.
Panel or microinverter?
Well, in this case, it's a panel.
Okay.
And that's why at solar noon, and we're assuming this is an STC day. So we're at 25 degrees Celsius and 1,000 watts per square meter. All right. So then if I have a 250 watt inverter, it's going to operate just like this, right?
Right.
And I'm going to get all of the power that's produced. So what happens if I have a 300 watt panel with a 250 watt microinverter? Well, that 350 watt panel is going to produce a curve that looks something like this.
Right.
Okay. Well, my inverter is going to clip off that amount of power. I'm not going to generate that power. It's going to be lost because my inverter can't handle it. But I'm going to gain all of this power.
Gotcha.
Okay.
So even on an STC day, I still come out ahead. But the fact is, 95% of the days, you're not producing STC quality, right? There's cloud cover,
Mhm.
it's warmer, it's cooler, whatever. So most of the time my curve is going to be somewhere down here. A lot of times it's going to be all jiggity jaggedy and everything. So you're not going to be at that limit anyway. So why not have the bigger inverter to handle on those lesser days? But even on a perfect day, I still come out ahead, because of the shoulders actually outperform what I'm losing. So economically, they found that a 1.3 ratio is typically going to be about the best. That's your inverter load ratio. Does that all make sense?
Yeah, pretty much. Yeah.
Yeah. Now, the microinverter people or the inverter companies always are telling you, go with a bigger array, go with a bigger array, because they're not paying for the panels.
Right.
So they
right.
don't care how much you paid for your panels. They just want to sell you an inverter,
Yeah.
So they're saying go with the bigger array. But you'll also see a lot of times in pricing of the panels, you could go with a bigger panel and it's not going to cost you much more just because of the weird pricing setup that they've got. So I might be able to buy a 350 watt panel for something very close to what I would pay for a 300 watt panel.
Right.
Well,
so
just
let me ask you this. So if you're like have a 350 watt panel and you have your microinverters are 280 or whatever, on the areas where it's clouded or a spot gets shaded, having those extra cells to get kind of make up for it is, I've always thought that's what clipping was. That's what I thought clipping was, but I was wrong.
No, it's because you're clipping off the
Right.
high end of production. That's where the term clipping comes from.
Right. I get it now. But with having those extra cells, wouldn't that give you like a little bit of extra, just a kind of reinforcement that inverter gets everything that it can get?
Yeah,
Okay.
that's why those shoulders are expanded. In low light
Right.
situations, you're getting more power.
Right.
Pretty much all day long, you're getting more power coming from
Right.
that. So, yep. So you're always going to be better off there. Let me see here. Jump back in. All right. It's been determined that a home requires a 6.5 kW array. The homeowner has purchased 26 Solar World 250 watt panels from her brother-in-law at her location. The temperature extremes are -37 and 43. The string inverter has an operating input range of 100 to 550 volts DC. Solar panel has the following characteristics: VOC of 37.8, coefficient 0.30, VMP 31.1, temperature coefficient 41 or 0.45% per degree Celsius. What is the maximum number of panels in each string? So
what kind of string?
this is probably one where you got lost for sure, right, Jake?
Yeah.
Yep.
You lost me. It has been determined.
Okay. So I'm going to write some of these down. 6.5 kW array, 26 250 watt panels, -37 degrees Celsius, 43 degrees Celsius, 100 to 550, and then it's VOC 37.8 volts, 0.3% per degree Celsius, BMP 31.1 volts, 0.45%. Okay, I'm writing them down so I can jump to my whiteboard. Okay, so it's asking us.
Can you give us your board one more time? I just want to write these down.
Okay, well, I'll walk through it. All right, so it's saying that we have a 6.5 kW array, right?
Yep.
And so what we're trying to determine is the string size.
how many modules on a string?
Yeah. So 250 watts for each module,
Okay.
for each panel. And it's saying, okay, what's the maximum in a string and what's the minimum in a string? That's what we're trying to figure out. Well, how do we start when we're doing these string calculations? First step for maximum, because they operate better when it's cold, I need the coldest temperature ever. Well, it just told me that's minus 37 degrees Celsius. So what is the difference between that and STC? So on a continuum here, if this is 0, we're at minus 37 and positive 25. So what is the delta or the difference? That's going to give us, what is it, 62 degrees? Right? It's 37 to get to 0, and then you add 25. So that's going to be 62 degrees difference.
63.
Everybody see how I got that?
63 degrees.
62, I think. 62 degrees from minus 37 to positive 25. There's 62 degrees there. Everybody clear?
Right.
Not
From
going to
zero-
proceed.
I'm sorry, from 0 to negative
No,
37.
we're going from negative 37 to positive 25. How
Okay.
many degrees between those two numbers?
Oh, never mind. Yeah, I
So
got
32 to 0 is 32, and then you add the 25.
37. Yeah,
30.
negative
Yeah, I'm
37.
sorry. Yeah.
So it's 62 degrees between those two numbers. That's how many degrees difference between those two, or delta. You good
Right.
now, Jimmy?
Yeah. I'm just
Okay.
going with it.
So then how much more voltage happens for every degree below standard test conditions? Because you increase the voltage for every degree. Well, the temperature coefficient was 0.30% per degree Celsius. So for every degree that I go down from 25, it's going to increase my production 0.3% per degree. So what is 62 degrees times 0.3?
What is 62?
18.6.
Yeah, so 62 times 0.3, it's telling me 18.6. So what that means is on the coldest day ever, that panel is going to produce 18.6% more volts than it would under standard test conditions. Is that clear?
So it's going to produce 18.6 more than 250.
No, that's watts. We're talking volts.
Oh, okay. I'm sorry.
So what is the worst,
I
or
don't
what's
remember
the
what the
most
voltage
volts?
was.
What's the most volts a panel can produce? It's VOC, theoretically, right?
Right,
Mhm.
right.
So this panel was 37.8 volts VOC. So I'm going to multiply that times 118.6%, right? 100% plus the 18.6%. Everybody clear?
Yeah.
Okay.
Because it's producing 18.6% more, but it's still producing 100%. It's just producing more. So how do I multiply? Well, I've got to change that percentage to 1.186. That's what it is in percentage wise. So 37.8 times 1.186 gives me
44.83.
Yep, 44.83. So it's telling me that on the coldest day ever, each of those panels might produce as much as 44.83 volts. Right?
Instead of the 37.8.
Right. That is because of the temperature adjustment, because it's cold. All right. So what is the maximum voltage the inverter can tolerate? Well, it just told me it was 550 volts. It's not 600, it's 550 volts is the maximum the inverter could tolerate. So I divide that by 44.83 volts, and we get
12.3,
yep,
12.27.
12.27, yeah. 12.27 panels max. Well, you can't have part of a panel. So do I
So
round
we're gonna
up
do
or down?
13.
Do I round
Oh.
up or down?
Oh, it
wanna
would be
s-
down because we don't
Oh.
want to go over that.
You're right. I want to stay below. So we're going to round. So it's 12 panels max.
Huh.
And that's the answer. That's your string answer.
Some of it.
Okay. We took the temperature difference between STC and the coldest temperature. We
Right.
found out how many degrees Celsius. We
Right.
multiplied that times the temperature coefficient at VOC, which was
Okay.
0.3. And we find on the coldest day, that panel might produce 18.6% more volts than it would at STC. So what is the maximum voltage it could produce at STC? It's 37.8 volts times 118.6%. So on the coldest day, that panel could produce 44.83 volts. I divide the inverter's tolerance, the maximum voltage the inverter can handle, by the maximum voltage on the coldest day. I find that we can hook 12.27 panels in a string, but I got to round down. So 12 panels max is my maximum string size.
Okay.
Right? Sort of makes
Yeah.
sense. After you review
Yeah, it
this
makes
video,
sense as you run through it, but as when I have to think it out myself, I'm not.
well, that's
I'm not
the
good at it.
problem.
That's my problem.
Yeah.
I can sit
Well-
here and do this all day.
Yeah, in today's world, 12 panels is going to be about the normal answer. 11, 12, 13.
Yeah, I
somewhere
know.
in
That's
there.
right. That's right. When you first said the question, I was in the other room. I was like, well, it's probably 12 panels on a string, because that's what we've talked about. I think that we've actually said that you could possibly get 13 on one.
It depends. It depends on the panel, but yeah.
Right.
All right. So then what's the minimum? Well, it's just kind of a backwards way of doing it is we say, all right, well, what's the hottest temperature ever? Well, in this case, they tell you it's 43 degrees. What is STC?
25.
25 degrees, but it's hotter. The panels are hotter than the ambient air temperature. So this is that thing that you have to remember. You add 25 degrees if it's ground mounted. You
Oh,
add 30 degrees if it's ballasted. And you add 35 degrees if it's flush to roof.
oh yeah, because that's the worst you can do.
Right. It's very hot up there. You guys were up on the roof with those panels. It's hotter up there than the ambient air temperature, right?
Dude, it was burning my ass.
Yeah,
'Cause I had to
Right.
sit on it.
that's right. So that's why you add it in. Well, this question says it's a ground mounted system. So I add back in 25 degrees Celsius because it's a ground mounted system. So we end up with a delta of 43 degrees Celsius. All right.
Okay.
So then I take that times the temperature coefficient. Well, in this case, because we're talking hottest, we don't go with the voltage, with the higher voltage. We go with the VMP, not VOC. Well, it
Okay.
said for the VMP, the temperature coefficient is 0.45% per degree Celsius. So we multiply 43 degrees Celsius times 0.45%, and we get
Where's the calculator, Randy?
19.35.
19.35%.
45%.
All right, now remember, when it's hotter, the panel is producing less voltage,
19 what?
right?
Yeah.
So it's 19.35% less than you would get at standard test conditions. So we take our VMP, which is the voltage that it's producing under normal conditions, and we would multiply it times 100%
31.
minus 19.35%, which equals 80.65%. Is that right?
I don't know.
What's 100 minus 19.35? It's going to be 80.65.
Yeah, 80.65.
So it's 80.65% or 0.8065. Because we're converting that percentage to a number. So we multiply 31.1 times 80 times 0.8065, and we get
25.08.
25.08, Randy said.
that sounds right, 25.08. 25.08 volts. So on the hottest day ever, that panel will produce only 25.8 volts. On the coldest day ever, that panel will produce 44.83 volts. Quite a difference. Well, now what we need to know is, what is the startup voltage of the inverter? Well, the question tells us it's 100, right? The inverter will start at 100 volts.
Okay.
Well, how many panels do we need to at least get that inverter started?
4 or 3.
Well, it's 3.9 something.
3.98. What is
Yeah.
that?
So we want to exceed 100. So in this case, we're going to round up. So it's going to be 4 panels minimum.
Okay. Okay.
Okay. So 12 panels max, 4 panels minimum. So review that, but let's jump in here and see if we're right. So we told 12 panels max. And it has all the math right here that we just did. And then it has 4 panels minimum.
There it is.
There you go.
Done all this before.
All right. So you guys are going to have to review this over and over and over, right?
Yeah, that might be the case, but we're getting together, I think Thursday or Friday. We've changed it to Friday morning, the 3 of us, and we're going to try to work some of these problems out. So
Okay. Well, hopefully you'll spend as much as you can. All right. When the DC power feeding an inverter is more than the inverter's rated capacity, the resulting power loss is referred to as
what is
This
this?
is a clipping.
clipping, right?
Yeah.
DC power feeding an inverter is more than the inverter can handle. Yeah, we just talked about that.
That's what we just
did.
want to.
Yeah.
Fluctuations in the DC waveform caused by connecting the DC system to the AC system are referred to as
A ripple.
ripple,
Ripple.
right?
Yeah.
Start to get that waveform in there in the DC. It's like an echo of the sine wave. The voltage at which grid inverter operates at its most efficient is known as
MPPT, voltage input range.
That's right. That's a It's a bad term, but that's what they call it.
It's horrible.
According to the NEC, when wire that is enclosed in PVC is buried in a trench, it must be located a minimum of
We know what this
18.
is going.
18 inches deep. Yeah, in Marietta, they wanted 24 inches deep.
They
but-
did want 24.
Oh, really?
Yeah,
Yeah.
but the minimum is 18 according to the NEC. Local jurisdictions can always go deeper, right? They can always require deeper. Which of the
Yeah, but-
following is not a common and legitimate reason for opting to make a supply side connection rather than a load side? The array is too small for a load side connection. There's no room in the service panel. The utility may require it, or the service panel is equipped with a GFPE breaker that does not allow backfeed.
Would it be the utility?
No, sometimes the utilities require it.
Did you go over this in the chapter?
Yeah, but typically it's smaller ones that are load side connected. So usually the issue is that the inverter or the array is too big. You know, you can't follow the 120% rule. You know, that's the thing, is if you have too big of an array, it's not going to allow you to connect to the load side. I mean, logically, if there's no breaker space in that load, in that service panel, you're not going to be able to make that connection. The utility may require it, and the backfeeding issue.
So A is the answer.
Yeah. When determining the ampacity rating of connection between the service entrance and the, you don't really have to worry about this, but it is the 10-foot tap rule. It's not going to be on the test. I don't know.
Right.
Jimmy,
But
do you ever
but-
deal with 10-foot and
Yeah.
25-foot tap rule?
10-foot. The 10-foot tap rule is, I mean, we're talking about like service entrance and stuff like that. The main,
Yeah.
like a meter.
Yep.
I mean, there's really nothing else that we tap off. We tap, except
Yeah,
maybe.
just for, it's, the rule is for sizing the wire. You know, what size wire is minimally required. Using a rough rule of thumb, how much space on a typical would be required for a typical roof for an 8 kW array? And the rule of thumb we're thinking here is it's basically you need, you can get 10 watts for every square foot. So if I've got an 8 kW array, what amount of roof space do I need?
The 800.
Right. So this is where you'll be asked this a lot. You know, let's say you've got a house and the south facing roof is 20 feet by 40 feet. You know,
Right.
well, that's 800 square feet. You could sort of look at that and go, you know, that can probably handle about an 8 kW array. It might be different because you've got vent pipes you got to work around, and you've got your setbacks, and you've got all of these others. And if there are dormers, it's going to be less. But your rough rule of thumb is 10 watts for every square foot. It's just a handy way of doing a quick assessment. Storing excess power generated by the PV array, and then using that power stored for periods of high cost would be known as?
Is that the shifting? We went over that a little bit ago with the
Shifting.
Yeah, load shifting. And that's it.
water heater.
Yep.
Yeah, me too.
Okay, well, that's a long time. It took us an hour and a half to get through all of these, but there you go. So everybody study this and over and over and over. So when you get together, that's going to be helpful. But if you can just sort of walk through them a few times until you understand, because some of this stuff is just going to be like Greek. And then at some point, you're going to go, oh, you know what? Now it makes sense.
Mhm.
So, you know,
Okay.
it's there's just nothing short of just doing it over and over until it just clicks, you know?
Yeah.
All right.
True.
Okay, well, that's good. If you have any questions, give me a call. And you said you're going to be studying on Friday, so you can give me a call or whatever,
Yeah.
or ask questions or text or whatever. And if you get stuck, and let me
Heather
know
took
you're going
off.
to do that.
Heather took off, but she wanted me to ask you a question real quick about PV Sketch. She wants to know when PV Sketch gives a cost proposal, does that include all materials, including the racking plus the labor?
Yeah, when we estimate like $3 a foot or $3 a
watt.
watt,
Right.
that's all in. That's everything. That's permitting. That's excavating. It's your install. It's everything. 100% of everything.
Okay.
All,
All right.
all your equipment, all of your profit, all of your design. It would be your final gross price there. So
Okay,
I just do a rough guess when I've been telling her in the assessments, let's do $3 a watt for this one. Let's do $2.75 a watt for this one. So, and that's just based on my guessing about how difficult that particular project, but I always want to overestimate. I'm not giving them a bid. I'm just trying to give them an idea. So
Right. Okay.
when you give them a bid, you better be a little more specific. So
I know. I'm
Yep.
trying to be.
There you go.
I don't want
All right.
to lose everything on one job.
Yeah. In fact, one of those jobs there, I was going to suggest you don't bid on the medical center here in Marietta. That's
Okay.
one that I just sent to her because
Oh,
it's
I
going
was
to be.
just at that the first settlement place.
Yeah.
I was just there the other day for my leg, and the doctor was chatting me up about solar. So
Yeah, the
fun.
one there on 2nd Street.
Yeah.
Well,
First settlement.
they use an average of about 50,000 kilowatt hours per month.
X-rays and MRIs.
Oh, I tell you, it's amazing, but it's going to be, that system is probably going to be more than 100 kilowatt hour or 100 kilowatt system.
Yeah.
It's going to be huge. So it's really something not to tackle early on in your career.
I think so. But man, if I did tackle it and it came out right, it would be a great, great check.
Yeah. Well,
so
get some experience under your belt before you start taking on jobs
that's
that size.
That's why we're doing residential and small farms.
Right. There you go. All right. I'll talk to you guys later.
All right. Thanks, man.
Bye-bye.
All right.